In today's episode, we'll take you behind the scenes for an exclusive look inside the MIT.nano cleanroom, where superconducting quantum chips, the so-called brain of a quantum computer, are designed and fabricated. Next, we'll get up close with the cryostat or chandelier, often referred to as the body of a quantum computer. Join us as we dive into the fascinating world of quantum technology with MIT students and researchers.
My name is Daniel Rodan-Legrain, and I'm a postdoc here in Will Oliver's group.
I'm a second-year grad student in Will Oliver's Engineering Quantum Systems group, and I work on 3D integration of superconducting qubits, which is one of the key technologies behind scaling towards a larger quantum computer.
My name is Pablo. I'm a first-year PhD student with Will Oliver's group, and my work has been mostly focused around fabricating qubits. We're trying to use novel materials for qubits such as graphene, which our group was the first to demonstrate making a qubit with. And a big part of that fabrication process happens in the clean room behind us that we will go into shortly.
Inside the cleanroom, building a superconducting quantum chip involves 3 key steps. First, a super thin layer of superconducting material is carefully deposited on the base, setting the foundation for nanoscale qubits. Next, using precise lithography, the circuit patterns are defined at the nanometer scale with any extra material removed to shape the design. Finally, the Josephson junction is created, a tiny dam between superconductors that allows just enough quantum flow to make quantum computing possible. Now, let's take a closer look at the machines behind this process and hear from the experts who bring superconducting quantum chips to life every day. We are finally in the clean room, it seems, in our bunny suits. We look lovely. So why don't you tell us what the space is about? What's happening?
So what is this? What is a clean room? Well, as its name indicates, it is a clean room. It's a room that is extremely clean. That one in particular is a clean room 100, which means that you have less than 100 particles, less than 500 nanometers, less than half a micron in diameter in a square feet, in a cubic feet of volume. So if you open, for example, your computer at home and you look at the fan, it's going to be full of dust. If we open a computer here inside the clean room, it's going to be pristinely clean. This is a tool where you don't want any hair, any piece of dead skin, any piece of particle to fall on your chips because they are already bigger than the chips we work with. So if one of those falls on your chip, then it can fail. We don't want anyone's hair to cost a Nobel Prize to any of the people here. So another thing that is very interesting about the clean room is that the airflow is regenerated every 15 seconds, so up to 250 times per hour. And this means that if someone is, for example, having a particle that is falling out of his hair, it will go in a laminate floor all the way down without being turbulent, without going into someone else's sample. So the reason we're wearing these bunny suits is not to protect you from the environment, it's to protect the environment from you. We don't want you to bring any particle from the outside, any dirt from the outside, any particular contaminant that can eventually damage the fabrication of the people working here with nano devices. Nano means 10 to the minus 9, which is basically around 100,000 times thinner than the diameter of a human hair. So the chips that people use to work here are on the order of a few nanometer size or bigger, but in any case, thinner than a human hair in most cases. The smaller you want to go in size, the bigger you need the machines, so to say, and that's why we have all these huge machines around us.
Yeah, no. So we are basically the danger, the threat. Right?
We are the danger to the environment, indeed. That's why we're all wearing in this bunny suit that we look like we're going into the moon.
Yes, well, I feel very good about it. So let's go and conquer the next device.
Let's do it.
Gabriel, what is this?
Yeah, so this is a blank silicon wafer. So this is what we start out with. We buy these silicon wafers from a company that sends us very high purity silicon. And just like any other computer chip, we start out with this blank thing and then coat it with metal using this tool behind us called the angstrom. And what it does is under a really high vacuum, it deposits metal by melting it and then letting it evaporate up onto the sample, which is mounted upside down. And what we do is we use something that's like a stencil. So if you were to spray paint a stencil, you would end up with a pattern, right? So what we do is we have some sort of stencil using something called photoresist, and then we deposit metal onto that stencil, and then we're left with a pattern. The pattern ends up looking something like one of these patterns on a chip here.
Oh, wow.
And then we cut it up into little pieces. So one of these little chips is what we would refer to as the processor. But obviously, many of these can fit onto a single silicon wafer. So we start out with these bare 2-inch wafers. We pattern it in the angstrom and other tools present in the clean room, and then we cut them up into our little chips that are quantum processors. So we have many different people in the group working on many different projects. We all have different designs that we want to test. So we might be able to fit on, tens of, if not hundreds of, depending on the size of the wafer, different designs onto this wafer, and that we're able to pattern at the same time. So we can go through hundreds of different designs at a time with a single wafer.
This is like a printer, like a pattern printing thing?
Yeah, basically.
Okay, is there a word for that? Or
Yeah, so the process that we go through is something called photolithography. And what this is we start out with a bare wafer that doesn't have anything on it. Then we write some sort of pattern, which is the stencil. And then we do what is the equivalent of what would be spray painting that stencil, which is evaporating metal onto it. So that is like the spray. The wafer itself is mounted upside down in this chamber. And then we use a beam of electrons that heats up a puck of metal, and then that metal evaporates onto the sample and paints where the stencil tells it to.
I see. Okay. So do you have your chips in there too?
Yeah. So here are some of my chips. I'm working on a piece of technology called 3D integration, and what we're doing is we're stacking smaller chips on top of a larger chip. So here, this is our first flip chip in the group, and so you can see this tiny chip was mounted upside down on top of this big one, and this is one of the key technologies behind building larger and larger quantum processor.
So we were saying before that the clean room is a very clean space, and this is where we want to have all our nanofabrication happening. But this tool that I have behind me is particularly special. It's like the Rolls Royce of evaporators for superconducting qubits. It has a very high vacuum inside it, and what is particular about it is that we only put the materials we want to put inside. So there is not what is called cross-contamination between different materials. To make an analogy with kitchen, for example, I care a lot about cross-contamination in kitchens between gluten-containing foods and gluten-free foods. Here is a little bit similar. If you have, for example, ferromagnets that go inside your materials, your superconducting qubits, those can cause the performance of the qubits to lower. So we only want to put certain materials, and this is why this tool is so well taken care of by our own group and another group that we collaborate with, Kevin O'Brien's group.
Okay, all right. So it does a great job of basically making sure that things that needs to be stay separate.
Exactly, this is exactly it. So for example, no chrome, no gold, no material that can go into other evaporators go into this particular tool that I have behind me.
Beautiful, thank you. You guys are like poets. Why is the light white, or it seems white here, but then yellow here?
Yes, so the part where the light is white, that are just like normal LEDs, but then in this part, the cleanroom light system has a special filter to filter out like some wavelengths of light, because in this part of the cleanroom we do the process called photolithography, which is used to define patterns on our chips. Basically, we start with a blank wafer, and then we want to cover it with a sort of stencil that allows us to print a pattern on the chip. And the way we do it is we cover all of it with resist, and then we use a tool that shines a very precise, very focused beam of light on some parts of the resist, and this causes changes in the molecular structure of the resist, and then we're able to remove those parts and leave the rest, and then we end up with a stencil made of resist on our chip or our wafer, and then we can take it into the evaporator tool, such as the angstrom that we saw earlier, and there you can deposit metal only on the parts of the wafer that have been exposed, and that way we can create a chip with the geometry that we want. And now if we try to do this in a normal room, simply the light coming in and touching, like hitting our sample would affect the resist and would like ruin the process. So we need to filter out certain wavelengths of light that have enough energy to affect our samples. So that is why we have this sort of orange filter in the lights in this room.
Interesting.
So this tool right here is the tool that takes the wafer and then on the computer you define the pattern that you want to print on your wafer, and then this tool is going to throw a beam of light at the wafer while it moves the stage to print the pattern that you have designed previously. And it is precise up to a few micrometers, so that is 10 to the minus 6 meters, which is extremely small, as you can imagine. And even sometimes if we want to go beyond that, we switch to something called electron beam lithography, because we reach a limit where light can actually diffract. Like at this scale, light can begin to diffract.
Okay, so this is how one of our qubits looks like. It's basically an aluminum circuit that is pre-patterned with the tools that Pablo was explaining you about and Gabe was explaining you about into this resonator. And this is what we use basically to read the qubit state, which will be what goes in the middle here. That is going to be the next step of our fabrication process. So this is how it looks like under high magnification in the microscope. By bare eye, you would not see, of course, this level of detail. And as we go smaller and smaller, you're going to be able to see more details. And our Josephson junction, which is the neuron, so to say, of our brain, is going to be tiny little small here at the center, with just a few tens of nanometers or hundreds of nanometers in size altogether. She's making a qubit with new materials. So the design differs from project to project. And basically, the design is something we do ourselves with a software. You can either do a code and program it with a code, or you can do it by kind of drawing the circuit. This is obviously done with a code so that everything is very, nanometrically designed, and then we simulate them multiple times. This is an iteration process. And once we're happy with the design we've made, we come here and we implement it. We make it happen using all the tools we have around us. It takes us several tens of steps to build it. It probably takes us a few days, if not weeks, to create a qubit from the design to the actual materialization of it. But when we have it and when we measure it, I would say it's very gratifying to see it work.
Yeah, definitely. So what makes a good chip?
So there are many definitions of what makes a good chip, and there is no one single criteria I could give you. But in general, from a fabrication point of view, we basically want the qubit to be as clean as possible, to have as minimal contaminants as possible. So for example, when you do the evaporation, you want to have a very high vacuum, because otherwise particle can go in between your metallic layers. And that will, of course, damage the performance of the qubit. So the way we measure the performance of a qubit is using what is called the T1 time, or the coherence time, which is basically to say how long can we control the qubit in an excited state versus a ground state, in the zero level to the ground level. And currently there is a very high interest in making qubits as long-lived as possible, while being able to scale them, while being able to control them simultaneously. So there are a lot of criterions that come into play when trying to build the best quantum computer possible.
And one PhD student likes to describe the quantum chip as the brain of the quantum computer.
Right, so you're talking about this analogy I like to use for how to understand a quantum computer. I like to think of it as like a human body, and there's the brain that does the thinking, it processes the information, and there's also other parts. There's a body that has blood vessels, it has neural paths. All that is in the other room we've seen with the cryostat, this thing we call BF4, that's all gold-plated. But here, this whole clean room, everything we've seen revolves around the brain part. It's the quantum chip. One could say it's the most critical, the most important part of the quantum computer. And the quantum chip, it contains all these patterns that we've seen are made at different stations. And here we're seeing a close-up of these patterns. And these patterns, these shapes, these metallic shapes, are responsible for processing information in our quantum computer. They are the ones that do sort of the magic. So if you're asking what's quantum about the quantum computer,
Yeah.
probably really where the most quantum physics happens is right here. And this is also where all of our, or most of our research is focused on, of all of us, is how do we improve the quantum physics that happens in this brain of the quantum computer? You know, what materials do we use? What shapes and patterns do we use? What processes, what recipes do we use to in these different tools? And so there's a lot of hard work going on to make this happen.
Yeah, no, absolutely. So kudos to you all. We can't touch
Virtual
each
high
other.
five.
Yeah, of course.
High five.
High five. There you go. Thanks, Shane.
High five.
Now let's go check out the body, the cryostats.
I am so excited to be here at the William Oliver Lab, and you guys are tackling the change of really cracking the code in quantum science. So let's go ahead and introduce ourselves.
Yeah, so I'm David, a PhD student in this group, moved from Europe, some PCs, some electronics, and our quantum computers over in that room, but we'll see that all in a minute.
This is the other quantum twin.
Exactly, David's twin brother. I'm Lucas, also a third year grad student here, and excited to be showing the lab to you guys today.
Hi, my name's Sarah. I'm in my final year of my PhD here, working on kind of like large quantum systems of many qubits, at least large for an academic group.
Yeah.
The wafers are at one point they are cut into chips, and these chips get put inside these packages.
Oh, okay.
And then we close them up, and we put them somewhere inside this.
And I'm holding a little box here in my hand that contains a quantum chip. And, you know, we've seen in the clean room how this chip is fabricated, what steps it undergoes. But importantly, as we finish fabricating the chip itself, maybe I can open it up. We see that the chip is in there. Importantly, we need to then package it. So we literally put it into this is gold-plated package. And we take this package and then we come over to the body, the way I like to think of it. So we have the brain and then this is the body, and we're gonna plug in this chip down here inside of this gray silver can. Right, yeah, so we would take this one off and we would screw it on here. And then we would connect the electrical outputs here, the ports and inputs. We would connect it to the wires coming down so that eventually we can control it from our computers. But so all in all, this completes the picture. We have sort of the brain embedded in this structure, which Sarah will explain us some more details of how it works. Basically, there's some cooling and some electrical components to it. And that completes the quantum computer.
Excellent. So why do you use gold?
You see the gold when you look at the chandelier, but what it actually is underneath that gold is copper. So it looks more like this color. And we use copper because it's a really good thermal conductor. The heat flows really, really efficiently through it. And when you're trying to cool something down from the temperature that we're currently at, which is about 300 Kelvin, we're trying to get to almost 0 Kelvin, which is absolute zero in temperature. Really, we operate around 20 millikelvins. But when we want to do this, we need to make sure that everything is at the exact same temperature when we're connected to something that's cooling that. So that's why we use copper. When we touch it, and it'll turn green, which is great for like the Statue of Liberty, something that's just artistic. But we have to make still thermal and electrical connections with the copper. And once that oxide forms, we can't do that as effectively.
So you know how people call this the chandelier, cryostat, and is this the actual quantum computer itself too? Like, do you call this the chandelier quantum computer?
I think it depends who's asking. I would probably say what David's holding in his hand is the quantum computer. It's like you have your computer and then you might have a monitor that you plug into it, but the actual computer is just that like little box.
Oh, interesting. So this is the quantum computer.
Yeah.
Huh. Interesting. And what are all these cables for?
These are all for control of the quantum computer. These can send radio frequency signals. So our quantum computers operate in the gigahertz range, which is about what your phone operates at or what your microwave operates at.
Unique about the BF4, and what's, I guess, unique about an MIT chandelier as opposed to other chandeliers out there?
This has multiple pulse tubes, which is what's used to cool down the cryostat to 4 Kelvin. And we also have multiple mixing chambers, which is what's used to cool down the cryostat to 20 millikelvin. We also have this high density wiring that side loads. So we can assemble this entire wiring assembly externally while we're operating the fridge. And then we can slot it in and cool it down. And that is a lot more effective than what we previously did, which was we'd have to get every individual cable and kind of like stick it in with everything already as it is here. And that would result in a lot of issues with those cables where we'd have an open, like an open circuit. And so we'd have to cool down the whole thing and measure it. And then we'd end up with like 1 or 2 broken cables. We'd warm back up and we'd do the same thing over and over again. So it would take forever to install the number of cables we have in this system.
Some of it is responsible to also create a vacuum or really an airtight exterior. And so we pump out all the air. There's a vacuum in here and then we cool it down. And a normal cycle, I guess, a normal day in the life of a PhD student would be to open up the fridge and take one of your, maybe you got a new chip from the fabrication team or you fabbed it yourself. And then you go in here, you install it, you connect all the electrical connections, then you do everything in reverse. You close up the cans and then you start the cooling process. So, if people ask me what I did at a given day in my week, I say I closed the fridge. And most people can do that, very quickly when they're getting their milk or something. I usually take up a day or so to close the fridge, but it's not an uncommon way to spend your day as a PhD student. So this is time well spent. What's interesting too is as we see quantum computers mature and grow, and also as companies start pursuing and developing them further, these sized fridges, although they're large for academic standards, they won't be large enough for an actual fully useful quantum computer. So if in however many years we have a quantum computer of this type, it will be much bigger and it won't fit into this fridge. So something we'll see for the quantum computers to come, I guess, is we'll see much larger fridges, much larger cooling infrastructure, and those already exist, but there will be even more. And then we'll have to get creative with how to fit more, how to make it bigger. Then the name of the game in quantum computing, like with any computing, is to scale up. The more the better. But the more the better means it's bigger, it's more expensive, right? And for us, bigger infrastructure, more work. So for us, some of the people like the fab guys and are looking into, can we make more qubits, more of these, crucial transistor-like features? Can we make more of them fit into a quantum chip? Can we make the quantum chip more compact? Or can we also find ways to make the wires more dense? You can see here that these wires over there on the left, they're very, very dense. They're a bit denser than the ones here on the right. And these are sort of the technological advancements that we're seeing and that we're going to have to see as we move to more mature quantum computers, really more practical quantum systems.
Useful and something that can be applicable to a lot of industries. So Lucas, earlier we've seen the chandelier and the many cables there. So where do all those cables actually lead to? Is it right here?
Yes, they actually come through the wall over there.
Okay.
Go through the back of the rack and then into these control electronics that we have over here. They're so-called arbitrary waveform generators. We call them AWGs. And they can generate arbitrary signals, pulse signals, that are then sent down these cables through the cryostat down to the chip. And by doing that, they actually control the components on the chip, the qubits, and ultimately this allows us to program the quantum computer and implement an algorithm of our choice. So I actually like to compare
creating a program for this to writing a musical score. When you're writing a musical score, like a piece of piano, you're creating a list of different frequencies that you want to play at different moments in time. This is exactly what we're doing here. We're creating a musical score that we're playing through these cables, and in doing so, implementing a quantum algorithm. We're looking at different kinds of quantum chips, comparing their behavior, and trying to tune them up and tune them to the best possible device performance. So that's what we mainly program.
Wow, that's amazing. Trailblazers, future makers, and I gotta say, the quantum twins are very good with their analogies. So thank you so much. Yes. Well, thank you.